take a look at this check on enthalpy of phase change. So in the first one, I've gone ahead and done this ahead of time. You want to draw and label the heating curve for water, and be sure to label enthalpies of phase change and their sign for delta H. And so here we have our heating curve. We've looked at this before, but now we want to look at it in terms of what's happening with the heat. And so heat of fusion for melting and heat of solidification for freezing, they're equal in magnitude but opposite in direction. And so heat of fusion is an endothermic process. We are absorbing energy in order to go ahead and melt, but it's going to be the opposite direction, or an exothermic process, when we're going to be freezing things. And so we're giving off energy if we are actually moving from the liquid to the solid, and that kind of is a different way of looking at these. Same thing goes with heat of vaporization for evaporation versus heat of condensation, and so they're equal in magnitude but opposite in direction. We can represent that graphically. So now we can actually do some conversions in order to be able to find out how much a particular amount of substance will either absorb or release heat. So in number 2, it says how much heat is required. So we want to know the heat that's required. So how much heat is required to vaporize? Okay, so that tells us that we're going to use the heat of vaporization, which we are given. Okay, and so we don't have to do anything else with that. We do need to go from grams into moles, and so we do need to know our molar mass. So let's do that first. So molar mass of methanol, which I didn't actually give you the formula for, so CH4O. I'll try to fix that in the master copy. And I've gone ahead and done that, and so it's 32 grams per mole. Okay. So now we're going to go ahead and do the conversion. So we're going to start off with our 40 grams. We're going to put in those 32 grams per 1 mole. And then for every 1 mole, we produce 35.2 kilojoules, or we absorb that much when we are changing phases. Okay. So let's do that. 40 grams times 35.2 divided by 32. And we end up with 44, so we have 3 sig figs, so we want to report that to 3 sig figs, so 44.0 kilojoules. Notice that this is a positive number, and that means that this value that we get is for an endothermic process. All right, let's take a look at the next one then. So in the next example, we are asked how much energy is released, and that makes sense. So if we require it, it's going to be absorbing it. So this one is how much energy is released. Oops, grab that. Energy is released. So we know that this should be an exothermic process. Okay, so that's a good double check on those. When we are freezing, and it gives us the heat of fusion. Okay, the problem is the heat of fusion is for melting. So fusion is for melting, but our process is freezing. So what do we need to do? We are going to have to find out what the difference is. So we know that the positive delta H of fusion is equal to the negative value for the delta H of solidification. Okay, and so that means that we want to use this number, but in the reverse. So we want to use negative 3.22 kilojoules per mole, okay, for freezing. All right, from there we can go ahead and do our conversion. So we still have the same molar mass that we're using. It's the same substance. And so we're going to use our 40 grams. For every 1 mole, we had 32 grams. And then for every 1 mole, we're going to have a negative 3.22 kilojoules. Let's go ahead and plug that in. So 40 times a negative 3.22 divided by 32. And that gives us negative 4.025. We have 3 sig figs still, so negative 4.03 kilojoules. Now, we said at the beginning that we should end up with an exothermic process, and it just so happens that this is a negative delta H, which is exothermic, or releasing, okay, releasing, and so that matches up.